All right, welcome everybody back to the COMSOC video seminar, to this new season for the new academic year. We've had a bit of a late start due to COMSOC and other events earlier this year, but I think we are back now in full force. We're planning to meet on Mondays, early Mondays in the month this year. Yeah, and the format has stayed the same. We will have 2 talks of 20 minutes each with 10 minutes of discussion, and then interrupted by a 10-minute coffee break that we will do in random breakout rooms where we can get to meet each other and talk a bit. So I'm very glad to welcome Ryoga Mahara to give the first talk today. He was going to give a presentation on the fair and efficient allocation of chores.
Yes, thank you for the introduction. Hello, everyone. I'm Ryoga from the University of Tokyo. I'm very happy to share my recent results with you. Today, I will talk about the existence of fair and efficient allocation of indivisible chores. And this paper will appear at SODA next year, and I'm really honored that this paper is selected as one of the best paper. Okay, so firstly, let me explain a brief overview of this work. In this work, we study the fair division problem of indivisible chores. And in this area, EF1 and PO are well-known concept as fairness and efficiency, respectively. And the major open problem in this area is whether an allocation that satisfies both EF1 and PO always exists. And in this work, we give a positive answer to this question. And more precisely, we show the existence of allocations that satisfy both EF1 and PO when each agent has an additive cost function. Okay, so our method is new in the sense that it combines a linear program, fixed point theorem, and a discrete algorithm in a very interesting way. Okay, so let's move on to the details. Okay, let me explain what the fair division problem of individual chores is. This is just an illustration, but the typical situation is a household chore in a shared house. Suppose that several people live together and they want to divide some chores. Oh, thank you. They want to divide some chores, such as laundry, cleaning the toilet, cleaning the bathroom, cleaning the kitchen, cooking, taking out the trash in a fair way. And the point here is that each agent has individual cost for each chores. This makes the problem very challenging. And given this situation, main questions are, what is a desirable allocation? Or does a desirable allocation always exist? Or can a desirable allocation be found efficiently? These are the typical main questions in fair division theory. And this kind of problem appears in many places in our societies. So we think that this is very natural and interesting problem. Okay, so let me explain our model. The instance R is given by a triple, and N is the set of agents numbered 1 to M, and M is the set of indivisible chores numbered 1 to M. And each agent I has an additive. Each agent I has a cost function Ci. This represents the cost for each agent when receiving a set of items. And in this work, we assume that each cost function is additive. So the cost of the subset S is the sum of the each cost J in S. Okay, so we can think the instance as being represented by a table like this. So this is an instance. And given an instance, our goal is to find a fair and efficient allocation A, where A is a tuple of A1 to AN, and each AI is a set of chores allocated to agent I. Okay. And we assume that all items are allocated. So in other words, each item must be allocated to exactly one agent. Okay. Yes. So next, let me explain the concept of fairness and efficiency, respectively. Okay, so MB fairness up to one item, EF1 for short, is the very, very studied fairness concept in the fair division theory. This is introduced by Budish in 2011. And Budish originally introduced the definition of EF1 for the setting of goods, but it can be extended to the setting of chores in a very natural way. And in EF1 allocation, no agent envies another agent if one chore is removed from their own bundle. So formally, we say that an allocation A is EF1 if for any pair of agent I and I prime, there exists a chore J in agent I's bundle, such that after removing the chore J from agent I's bundle, then the cost of this bundle is at the most the cost of agent I prime's bundle. In other words, agent I does not envy agent I prime when removing the chore J from agent I's bundle. Okay, this is a definition of EF1. And the important fact is that EF1 allocations always exist for any instance and can be computed in polynomial time. This is a very well-known result in fair division theory. Next, let me explain the efficiency concept called Pareto optimality. This is a very standard concept in economics, and it has been used for a long time. In Pareto optimal allocation, it's no longer possible to make someone better off without making someone else worse off. Okay, so formally, we define the Pareto optimality as follows. We say that an allocation Y Pareto dominates allocation X if for any pair, any agent I, the cost of Yi is at the most the cost of Xi, which means that no one is worse off. And there exists an agent I prime such that the cost of Yi prime is at the strictly smaller than the cost of Xi prime, which means that someone is strictly better off. Okay. Then we define the Pareto optimality as follows. We say that an allocation A is Pareto optimal if allocation A is not Pareto dominated by any other allocation. Okay, this is a definition of Pareto optimality. Okay, next let me explain the fractional Pareto optimality, which is a generalization of the standard Pareto optimality. This concept extends the standard Pareto optimality to the convex combinations of multiple integral allocations. And the formal definition is following, but in this talk, there's no need to read the formal definition because as I will explain later, actually FPO has a good characterization that I will use in this study. So there's no need to read the formal definition here. But the important facts are as follows. Firstly, FPO implies PO. So every FPO allocation satisfies Pareto optimality. And secondly, FPO or PO allocations always exist. And one such an allocation can be computed in polynomial time. And finally, as I will explain later, FPO has a good characterization that I will use in this study. And actually, this FPO is the easier to deal with than standard PO. So this is the reason why I introduced this concept here. Okay, let's look at the following simple example. This is the instance, 3 agent and 3 items. And if we allocate the chore 2 to agent 1, chore 3 to agent 2, and so on, so this allocation satisfies EF1. We can easily check this, but not PO, but not satisfy PO, because this allocation is Pareto dominated by the rightmost allocation. Okay. On the other hand, if we allocate every chores to agent 1, and this allocation satisfies PO, but not EF1. Okay. And in this figure, if we allocate the chores in this way, this allocation satisfies EF1 and PO. Okay. So the very natural question is whether an allocation that satisfies both EF1 and PO always exists. Here are previous work on the existence of EF1 plus PO allocations. And in every previous work, they showed the existence of EF1 plus PO allocations in restricted instances. Okay. For example, if we restrict the number of agents, the existence has shown for 2 or 3 agents. And for example, if we restrict the type of cost functions, the existence has shown for 1 type or 2 types or 3 types. And there are results for binary cost functions or 2 types of chores. And all the above results also design polynomial time algorithms together with existence results. Okay. So because of this situation, the major open question is whether an EF1 plus P allocation always exists. So here are our contributions in this work. We show the existence of EF1 and PO allocations when each agent has an additive cost function. And we also show the existence of EF1 plus FPO allocations in the same settings. So this is a bit stronger results than the first results. Okay. And we also design a polynomial time algorithm that computes an EF1 plus PO allocation when the number of agents is constant. And finally, we extend all the above results to the more general setting of weighted EF1, which is a generalization of the standard EF1. And this is our contributions. Okay, and in the remaining time, I will explain how we show the first main results. And in this talk, we don't go into the details other results 2, 3, 4, because they are relatively easily followed from the first main results. Okay. Okay, so now let me explain how we show the existence of EF1 plus PO allocation. Okay, so firstly, given an instance I, we slightly perturb the cost function of each agent, and we create a non-degenerate instance. We don't define the non-degenerate instance here, but this is just an instance that satisfies some useful property. And then we show the existence of EF1 plus FPO allocation in this non-degenerate instance. And if the perturbation parameter epsilon is sufficiently small, then we can show that this allocation satisfies EF1 plus PO in the original instance. Okay. So our goal is to show the existence of an EF1 plus FPO allocation in non-degenerate instances. Okay. Okay. So next, let me explain the characterization of FPO allocations. This is very classical results in economics. And so an allocation A is FPO if and only if the following hold. There exists a positive weight vector W such that the allocation A is an allocation minimizing this weighted social cost function. And this optimization problem can be written as a linear program, LPW, like this. So we can restate this statement to an allocation A is an optimal allocation to LPW. Okay. And if we write the dual problem of LPW, then we obtain the dual LPW for like this. And each dual variable pj can be interpreted as the price of each item j. And the complementary slackness condition is following. And the one useful property is that dual LPW has a unique optimal solution. Because in this optimization problem, this maximizes the sum of each pj, and each pj is bounded above. So the optimal solution is optimal solution sets each pj to the type possible bound. So the LP has a unique optimal solution. Okay. So next, let me explain the very useful concept called price EF1. PEF1 for short. This concept was introduced by Berman and others. And this concept has been used in most previous work, both for goods and chores. Okay, so given an allocation A and the price vector P, the price EF1 is defined as follows. This is very similar to the definition of standard EF1. But the only difference is that this is not a cost function, and we use this price vector instead of cost function. Okay, this is a definition of PEF1. Okay, so and the important lemma, the important factor is the following lemma. Okay, let's say that an A and P be optimal solutions to LPW and dual LPW respectively. And if A is the PF1 allocation, then A is also EF1 allocation. And this lemma can be proved by using complementary slackness condition and the dual feasibility. And this is very useful lemma. So combining the characterization of FPO and this lemma, our goal is to find a positive weight vector W and an allocation A that satisfy A is an optimal allocation to LPW, and A is a price EF1 allocation. Okay, so once we obtain the positive weight vector W and allocation A that satisfies these conditions, we can conclude that this allocation A satisfies EF1 and FPO, so we are done. Okay. So next, let me explain how we guarantee this desirable weight vector W. Okay, so in order to guarantee the existence of such a desirable weight vector W, we apply the fixed point theorem called KKM lemma. We can see this as a set covering version of Sperner's lemma. Okay, so this is a statement of KKM lemma, and let delta n-1 be a n-1 dimensional standard simplex. And let C1 to Cn be closed sets on this simplex. And for any point W in this simplex, there exists an index I such that Wi is positive, and this point is in Ci. This is an assumption of KKM lemma. Then the claim of KKM lemma is that the intersection of each Ci is non-empty. Okay, so this is a statement of KKM lemma that I will use. Okay, so let me explain how to guarantee such a desirable weight vector W by using KKM lemma. Okay, so we fix any agent I, and we define Ci as follows. Ci is a set of all point W in this simplex such that for some optimal allocation A to LPW and the unique optimal solution P to dual LPW, agent I is price NB free. In other words, the price of agent I's bundle is at most the price of any other agent's bundle. Okay, so this is a definition of price NB free. And if we define each Ci in this way, we can show that each Ci is closed and each Ci satisfy satisfies KKM covering conditions, so we can apply the KKM lemma to these CI. Then we obtain the following lemma. This lemma says that there exists a point W in this simplex such that for every agent I, there exists an optimal allocation A to LPW such that agent I is price NB free with respect to this allocation A and unique optimal solution P. Okay. So we want to say that this weight vector W as a desirable positive weight vector, but there is one issue here. The component of W might be 0. Okay. So we cannot guarantee the W as a positive weight vector. But this problem can be handled by considering the slightly shrunk simplex at first. So this is a very technical part. So I don't explain the details here, but we can conclude that there exists a positive weight vector W such that the following conditions hold. Okay, we call this lemma X. And what exactly does lemma X say? Actually, by using complementary slackness condition, we can restate this lemma X in a more clear form. Okay, so W is the weight vector satisfying the conditions of lemma X, and P is the unique optimal solution to the W, and we define the following graph G with respect to W and P. G is a bipartite graph between agents and chores, and we define the H from I to J if these conditions hold. Okay, recall that the complementary slackness condition is following. So by using these facts, we can restate the lemma X as follows. For any agent I, if chores are allocated appropriately along the edges of this graph G, then agent I can be made price NB free. Yeah, this is a restatement of lemma X. So let's look at this example. Okay, so consider agent 1. If we allocate every chores in this way, agent 1 becomes price NB free. Okay, so if we consider this agent 2, if we allocate the items in this way, agent 2 becomes price NB free. And if we consider this agent 3, if we allocate each items in this way, agent 3 becomes price NB free. So this graph satisfies the conditions of lemma X. This is the conditions. Okay. And remember that we are considering the non-degenerate instance. So actually, for non-degenerate instance, this graph G is always a forest. Okay. This can be proved by using the definitions of non-degenerate instance. Okay, so combining this lemma and the conditions of lemma X, we can conclude that the following lemma Y. The lemma Y says that for non-degenerate instance, if chores are allocated appropriately along the edges of graph G, then we can obtain a price EF1 allocation. So this allocation satisfies PF1, and since we use the positive weight vector W, so this allocation A is an optimal allocation to LPW. So this allocation satisfies EF1 and FPO in non-degenerate instance. Okay, so we are done. This is a very quick overview of our first main results. Okay. Okay, so now let me summarize in my talk. In this study, in this work, we studied the fair division problem of individual chores, and here are our contributions. And there are many future directions related to our work. And the most important part in this work is to combine fixed point theorem and the discrete algorithm in a very interesting way. So I hope that our approach will inspire further research on other fair division problem, or even on algorithmic game theory problem. Okay, that's all. Thank you for your attention.
Thank you very much. Let's unmute and give our speaker a round of applause. Okay, if you have any questions, please write them in the chat or select the raised hand emoji. Okay, I don't see any questions yet. So maybe you can you talk a bit more about the future work? For example, polynomial time algorithm, is that something that seems plausible to do without somehow finding a different technique that doesn't use fixed point?
Yeah. So our existence result relies on using fixed point theorem. So it seems very challenging to construct a polynomial algorithm to find EF1 plus PO allocations. And if we want to construct a polynomial some algorithm to find EF1 plus PO, then we need to change prices of items. But such a technique is very difficult because changing the prices or reallocating items does not help the terminations or does not help the improvement of potential function, right? So this seems very challenging.
Jan?
Yeah, so maybe that's just my missing understanding of the fixed point theorem. But can you, so you don't have a polynomial time algorithm, but
Yes.
does your theorem give rise to an algorithm that, like how bad would it be to implement your algorithm in practice is maybe my question. So dropping the polynomial time, in practice, could you actually implement this algorithm to give results, or is this really more to be seen as an existence result?
In practice, we can construct some algorithm, and I've tried it by using computer PC, and I found that for every instance that algorithm terminates, and it finds EF1 plus P allocations. But yeah, so in practice we can find. I hope that we can find almost for every allocation, for every instance, we can find EF1 plus P allocations. Yeah.
Cool, thank you.
At least for small instances.
Yes, thank you.
Okay, I'll ask another question. Can you give a bit more intuition for the non-degenerate instance thing? Why is it necessary? And is there any intuition behind it?
Yeah, I have the definition of non-degenerate instance, but this is, yeah, I want to do it. Actually, I have no intuition by using. This is very mysterious. But I have a counterexample. If G has a cycle, then we cannot prove this lemma Y in such an instance. So the non-degeneracy is somewhat essential in our proof. But yeah, I have no intuition actually. Yeah, that's a very interesting question.
Okay, Nisak, do you want to speak, or should I?
Oh, it's not a question. It was just a comment on the previous in practice thing that in practice, if you want EF1 plus PO for chores, then split it employs a different algorithm that came from a paper of mine with Dominic and Surush, which is EF1 plus PO if it terminates, and seems to have always terminated so far in practice. So, yeah. And we are glad to see that now EF1 plus PO is known to exist. So.
I guess Sid is asking a question to Nisarg whether this implementation works for mixed manner.
I think it might be for yoga.
No. Maybe.
Sid, do you want to unmute and ask?
I have never tried this for mixed setting.
Right.
Oh yeah.
That's split.
Okay. Yeah, we haven't thought about it. Will definitely require non-trivial extension.
Yeah, I think so.
Yeah.
Okay. I think I did not miss any questions. Last chance. Otherwise, let's thank Ryoga again.
Thank you.
Thank you. And now it's time for our break. We will have a 10-minute break where you will be assigned to random breakout rooms. If you like, you're very welcome to join and chat to people. Otherwise, we will be back at 45 past the hour for our second talk. Okay, people are back from the breakout rooms. Welcome back to the second half of the seminar, where we will hear from Maly talking about the core in participatory budgeting.
So yeah, hello everyone. Today I'm going to talk about the core in participatory budgeting, and in particular the fact that it can be empty. And to do that, I'll first talk a bit about participatory budgeting, then the core, then I'll describe why it can be empty, and finally I'll discuss the results very briefly. Now, for the introduction to participatory budgeting, I think most of you will know most of the things I'm going to say, so I'll try to be brief and maybe also throw in a few facts that not everyone knows. So first, what is participatory budgeting? It's a relatively new democratic process where the city allocates a certain amount of budget to the participatory process. Then citizens can propose projects, and in a second stage, citizens can decide which projects should be implemented. So maybe the things I want to highlight here is that in comparison to many other models we look into in COMSOC, this is really motivated by a real-world application. So really thousands of cities worldwide do participatory budgeting. And secondly, something we sometimes forget, it really is a multi-stage process, and we essentially only look at the second stage in computational social choice because that's the collective choice problem. But if you talk to practitioners and political scientists, they're often much more interested in the other stages. So while what we do is modeled on reality, it's also important to remember that this is not the only part of participatory budgeting that might be interesting. But for now, let's focus on this second stage and ask ourselves, how do people actually make this decision? Well, originally in Brazil, and still today in most of the developing nations, they just meet in person and they make the decision then and there, either by raising their hand or maybe even by discussing until they find a unanimous decision. In developed nations like Europe and the US, it's much more common to see voting. So that's much more interesting for COMSOC, of course. And in particular in Europe, we mostly see e-voting, which is very useful because it means we can actually implement pretty complicated voting algorithms if we come up with them. So this makes PB, in particular in Europe, very interesting application ground for COMSOC. And indeed, some cities in Europe actually use very interesting new voting rules that people from our community designed. So does also the question maybe, does participatory budgeting work? Does it actually benefit the people in the community? And at least for developing nations, there is very strong evidence of positive societal effects. There is a famous paper by, or book even by Brian Wampler, who shows in Brazil really outstanding effects of PB, though I've been told by other political scientists that we should take these numbers with a big grain of salt. But I think generally the directionality everyone agrees on. In developed nations, there is much less research on this, but there is still some evidence that PB can, for example, increase trust in governments or reduce populist attitudes. So yeah, I think that for me is a good reason to study PB, because it actually is a process that can change how people feel about politics. And now in order to study it with our tools, we first have to model it mathematically. And to do that, let's maybe look at a ballot that is used in participatory budgeting. And so, okay, so first part of participatory budgeting, as I said before, the city defines how much budget is allocated to this process. So first we have a budget. And then if we look at this ballot, there are a lot of different projects. And it's very small, but for each project, there is the list of the cost of implementing it listed. And then voters vote by ticking these checkboxes to approve a project. So the voting is approval voting. And so to put this into a mathematical model, any PB instance is a set of voters N, a set of projects P, a cost function P that maps each project to its cost. We have a budget B, and for every voter, we have a ballot, which is just a set of projects. And then a rule is just maps the PB instance to a feasible set of projects. And so my first contribution in this talk is to tell you that we can also visualize these instances very differently by not looking at a table as we usually do, but by looking at a graph. So it's just the incidence graph of the PB instance. So for each project, we have a box that contains its cost. And then for each voter, we have a circle, and a voter is connected to a project if they approve it. And so for this instance, I think this is not very meaningful, this graph, but we'll see later that this graph representation can maybe give us some intuition why certain proofs work in a better way than a table can. And now the final ingredient that we need is to figure out how we judge the quality of an outcome. Because now we have a model of PB, but what do we actually want the outcome to be like? And this is actually a very hard question. So in particular, even if we have one voter, it's not quite clear what kind of outcome we want. So if we look at this PB instance, we have a budget of 100, and we have these 3 projects, and our one voter approves all of them. Well, do they prefer to have 2 projects, even if that means less money is spent on the projects that they like, or would they prefer the big project? It's probably not quite clear what to pick here. So yeah, that's a hard problem. And to some extent, we try to avoid this by just modeling satisfaction very generally. So what we can do is we can just assign every voter for every set of project a positive utility for that bundle of project. That's probably too general to do anything, so maybe we want to at least assume additivity. And in particular, if you're only given approval ballots, I would argue what we actually want to assume is, oh, I forgot a line there. In approval-based PB, we can assume that there is such as a function SUT, such that the utility of every agent is just the intersection of the bundle with the projects that they approve. So their utility only depends on which of the approved projects their approved projects have been funded, because that's the only information we are given. And the standard approach we mostly see in most papers now is to just take the sum of all the cost of all the approved projects in the outcome. So we assume that we can measure your utility by figuring out how much money was spent on projects you liked. However, there is one main alternative, which is to just count the number of projects that you approved which have been funded. In my opinion, both kind of make sense. I tend to prefer the first one, but I mean, the second one certainly isn't completely stupid either. Then there are a lot of other alternatives. Two I wanted to quickly mention. Oh, there's the line I've been missing. The first one is the Chamberlain-Courant satisfaction function, which basically says I have a satisfaction of 1 if any project I like has been funded, and I have a satisfaction of 0 if none of the projects I like have been funded. So this is a pretty extreme, I'm either happy or unhappy. And then there are a lot of ways of doing something that's kind of in between cost and cardinality. So anything where I discount higher costs, I can, for example, take the square root of the cost or the logarithm to kind of have something that's in between the taking the full cost or taking just the number of projects. So that's how we measure satisfaction. And now, for very general satisfaction functions, what is the core that I'm going to talk about? So we say for any satisfaction function, a comma TW is in the core if there is no group of voters n prime and set of candidates c prime, such that the voters in n prime could afford the projects c prime with the amount of money that they deserve. So the percentage of budget equivalent to the percentage of the population they make up to can buy all the projects in C prime. And secondly, the outcome C prime is preferred to the actual outcome by all voters in N prime. So that you can kind of think of this as a very strong equilibrium notion where the voters in N prime, they can deviate to C prime, and that's a profitable deviation for them, even if all the remaining voters just don't fund any projects anymore. So this is a pretty strong equilibrium notion. And yeah, so we could use this to define desirable outcomes. So intuitively, if something is in the core, it's fair because no group of voters is so underrepresented that they'd rather take their part of the budget and do something else. So this is a nice notion. It just has one problem. In full generality, it's impossible to satisfy it. So if we take arbitrary satisfaction functions, then it has been known that the core can be empty since 2018. And we can look at this example. Here I changed my notation slightly to say that a solid line means voter I likes project 1 a lot, and a dashed line means they like this project a bit. And so in particular, they like it less than the project to which they have a solid line. And then we have a budget of 3, so we can fund 3 of these projects. You can convince yourself that all possible allocations of 3 projects are symmetric, so we just look at 1. And now I claim for this allocation, there is a way to deviate for voters 1 and 3. In particular, voters 1 and 3 can fund this project up here with their part of the budget, because there are 2 voters, the budget is 3, and there are a total of 6 voters, so 2 voters deserve 1 budget, 1/3 of the budget. So they can fund this project up here, and that's an improvement for voter 3 because before he didn't like anything, and now he at least gets the project they like a bit, and voter 1 gets now the project they like more than the project they had before. Okay, so for general utility functions, we cannot satisfy the core. However, what's the status for approval-based satisfaction functions? So we at least assume that the satisfaction only depends on approvals. This is very important because in reality, essentially all PV instances are approval-based. So we're really interested in how it looks like there. And we see that this example doesn't work here because two voters have different levels of satisfaction for the same project, which is not possible under approval satisfaction functions. So maybe slightly more motivation why we care about this. This is a finger of all the proportionality notions we could collect in 2023. And for all of them, we knew whether they're satisfiable or not, except for the core. So that's just what we want to know because it's open motivation. And then the other motivation is extended justified representation, which is arguably the most important proportionality notion in participatory budgeting. And this combines the idea of so-called justified representation and the core, and in particular, in a formal sense, it's a restriction of the core to so-called cohesive groups. And so why should we be interested in extended justified representation instead of the core? If the core would be satisfiable, this would be a bit weird to restrict it. So maybe to make EJR more justified, it would be nice to show that the core is not achievable. And that's exactly what I found recently an example for. Let me show you the example for the cost satisfaction function. So we have 9 projects, 3 voters, and a budget of 9. And first, I want to claim that we have to fund at least one of these projects worth 5 in the middle. To show this, assume we fund only the outer projects, which we can't fund all of them, but say we did. Then still voter 1 and 3 would be better off together funding the 5 project, which they can also afford because together they deserve a budget of 6. So for them, this is already a blocking coalition. So we have to fund at least one of the inner projects. Now we have 4 money left. Next, we see that we need to give voter 2 at least their big project because they deserve 3 budgets. So we have to give them their big project. Otherwise, they could deviate to that. And then we can have 1 more money left. It really doesn't matter where we put this. For convenience, we put it here, but it's easy to see that it doesn't matter. And now I claim that 2 and 3 together can deviate. So why can they do this? Well, 2 would like to have this project worth 5 no matter what. 3 already has 5 utility, but together 2 and 3 have 6 utility, 6 budget. So 2 could say, well, we fund also your project worth 1 over here. And then this would be a better outcome for voter 3 as well. So they can deviate to this. So in this example, the core is empty for the cost satisfaction function. Now we can make this also a bit more general if we would like to. I think for time reasons, I don't go through the full theory statement, but in the paper you can find the statement which makes some assumptions on the satisfaction function and then shows that if all of these assumptions hold, then the proof works in a more general setting. So in particular, we need that having more projects is better. We need that more expensive projects are more desirable. And then we need some conditions that tell us if we have a project worth epsilon, then adding this to a second project is worse than just having a much more expensive project, at least for some values of budget and epsilon. And then we can just turn our example into this more general setting, and you can see that the same counterexample actually still holds. So maybe let me discuss the implications of this result very quickly. So the theorem I showed you applied to SAT cost. We've seen this, I've shown you this directly, but the theorem reproves that the core can be empty for the cost satisfaction function. Moreover, it basically applies to any cost-based satisfaction function that I could come up with, in particular anything that kind of models decreasing marginal utilities. It does not apply to the Chamberlain-Courant satisfaction function. This is the case because we require for the proof that more projects is strictly better than less projects. And also it makes sense because for the Chamberlain-Courant satisfaction function, the core can actually never be empty as it's implied by justified representation, a weaker axiom that we know to be satisfiable. And finally, the theorem also does not apply to the cardinal satisfaction function. And here, this is really, I have no idea how to extend it to the cardinal satisfaction function. Why is this difficult? Well, because if we look at this example, what we needed in the beginning was that the projects in the middle are more valuable than the outer projects. And if all projects are the same, this does not work anymore. One idea you could have is to just add more projects in the middle to make collaboration still more interesting than funding your own projects. And actually, if you look at this example and you kind of copy the allocation we had before, you can convince yourself that 2 and 3 are still a blocking pair. So this looks quite good. Somehow we could generalize this to the cardinal satisfaction function. However, by adding additional projects, we also added one other possible outcome. And this is this one, where we fund one joint project for all of the 3 agents. And this outcome is actually in the core, because now every voter has a utility of 5 already, and that's enough for no one to wanting to deviate. And then the last point I wanted to make is, in some sense, all the counterexamples are based on the idea that you can pull someone away, or you can improve your utility because someone is so desperate to work with you that they give you more than you deserve. And this we can also make into a point about whether the core actually is a good fairness notion. So if we look at this example, this allocation is in the core. So we have to decide again onto one of the big projects to fund. We give voter 3 everything they want to make up for them not having a big project. And then we give voter 1 their bigger project. However, if we I would argue it would look more fair to do this, because this coalition, they together want to fund projects. Why should only the middle voter get their big project and voter 2 get nothing? Well, because this is not in the core anymore, because now voter 1 can leave the coalition with voter 2 and go to the coalition with voter 3 and tell them, well, we do our joint project if you give me more than my share of our joint budget. This cannot happen under cohesive deviations. So this is actually an argument why EJR might make even more sense than the core, though you could probably also find other ways to define well, versions of the core that force some form of like a fair distribution of the funds that the deviating group has. And that's all I wanted to say today. So in this paper I talked about, we settled the question of the emptiness of the core for basically all natural satisfaction functions except the cardinal satisfaction function. This is very important because the question is also open in multi-winner voting, whether the core is always non-empty. And to make any progress there, we probably first need to understand the cardinal satisfaction function. That's probably a next step if you want to make any progress. There's also a recent paper by Dominic that shows that if there exists a counterexample for multi-winner voting, it has to be quite large. So it will definitely not be as nice and neat as the counterexample we've seen today. And then the last example shows that it could also just make sense to introduce a version of the core that requires more equal contributions to make to avoid these cases where just being more central means you get more a better outcome, even though you might not deserve this. Yeah, that's it.
Thank you very much. Let's thank our speaker. This is a new animation with the emojis that are floating up.
Yes.
It looks very fancy. Right. Peter has a question.
Yes, a rather simple one. If you look at the collection of counterexamples where the core is empty, if you take one and disturb it a little bit, does it remain a counterexample or may it depend on strict equalities of the various cost functions? So is it open?
So I think for strict equality, no, I think it really doesn't matter. I think it mainly depends on the order of the projects here. You kind of need, I mean, yeah, you need that like the right sets of projects are not jointly affordable, and you need the inner projects to be more desirable than the outer projects. So I would be very surprised if, so it shouldn't require like exact equalities. I mean, of course, if you change it too much, so different sets of projects become affordable together, then you might run into problems. But I think by
So the collection of counterexample is most likely to be open topologically.
Yes, yeah, I think
Thanks.
so.
Okay, make yourself known if you have other questions. Otherwise, oh yeah, Bill has a question.
Yeah, so it seems to me, can you hear me?
Yes.
Yes.
It seems to me the answer to that question would be easy by taking the payoff functions, perturbing them by some essentially irrational amounts, tiny irrational amounts. They still meet the conditions that Jan stated, and then you never get any equalities ever. No?
Yes, yeah. I think that should be correct.
I have a question. Have you thought about whether this example is minimal in any ways? So number of projects, number of different cost levels. So there are 1, 3, and 5. Does it have to go all the way up to 5, or is smaller possible?
I mean, I'm pretty sure it's minimal in the number of voters, but it's not too much. No, otherwise, I would actually, okay. I mean, originally I thought it already works with 6 projects. And so I was slightly annoyed that I have to have 2 own projects per voter. Maybe if you're a bit more clever, you can avoid this. This is basically just to make sure that there's not like the budget fits and everything. So yeah, it could be that less projects work, but I don't exactly see how you would do that. I tried to reduce it for aesthetic reasons and I failed, but that's obviously not a proof that it's not possible.
And in your argument, you did not reason about the grand coalition, right? It was only singletons and pairs that were deviating. Yes. Okay, Anton has a question.
Hi, Jan.
Hi.
I was wondering, given this non-existence example, does that tell us anything about where we should be looking for, like, the frontier of what is satisfiable in participatory budgeting? Should we be looking at some kind of like core up to 1 project or core up to any project style notion? Could there be something between core and FJR in the diagram you had?
Yeah, so that's a good question. So I thought a bit about not up to 1 approximations, but like multiplicative approximations. And there I don't see that the counterexample puts any real limit on approximatability. So yeah, I guess the answer is I don't know. I tried to make the example a bit more like biting in this direction, and I haven't had much success so far. So to me, it seems to mostly show that exactly this notion of core is not satisfiable. mean, at least in this example, core up to 1 should be satisfiable, but I also wouldn't be surprised if you can just add a few projects. I don't know, but it's a very good question. But yeah, also as I hinted at, I think I would be even more interested in coming up with something that is somewhere between cohesiveness and the like full anything goes of the core, because I actually do think by now that the core allows deviations that are not really increasing fairness. But cohesiveness is a very strong restriction on the core. So it would be interesting to see whether we can make something happen that it's a weaker sensibility notion on the deviation and is still satisfiable.
Okay, are there further questions? Doesn't seem like it. Then let's thank Jan one more time using the fancy emojis if you can find them. All right, thanks everyone for coming. We have a preliminary plan for the next seminar on the 1st of December, and we will announce the speakers for that soon. And have a nice rest of your day. Bye.
Bye-bye.